but New York City is under assault. Near our offices near Lincoln Center, there's a crane that's dangling apparently. And then my laboratory up at the near the Columbian Medical Center, it's just blowing like mad, and everything is just in turbulence. So I'm actually very glad, even though it's foggy right now. I have to raise my hand. I'm a reformed biotech CEO and pharma executive. So I'm going to tell you, I'm not going to tell you, I'm not looking for any money. I'm not asking for anybody to invest. I'm just telling you a story about a foundation that I work for and how we've taken this foundation to a level that I think would be very interesting to many of you. We're using stem cell technology to accelerate cures. This foundation was founded in 2006 by Susan Solomon. And Susan, who was a big advocate of stem cell research and was very instrumental in the whole lobbying and everything behind the scenes in the government political environment. And I think Bernie, the Genetic Policy Institute, is honoring her for her long-standing work in advocating for stem cell research. The foundation is really divided into two things, the foundation and the research institute. I'll talk primarily about the research institute, but I have to touch on the foundation's work, what we do. We give money away. We also do things where we hold and educate within the New York area. We have panels, we have a meeting. We just had a great translational meeting. It was oversold. I think 500 people tried to come to this meeting, and we can only hold 450, and that was in New York City. It was purely related to stem cell translation. It's held at Rockefeller University. We also have a program that's fairly unique. We have over the last several years funded now 30, 40 postdoctoral candidates, and they're high-value candidates. Many of them now, the first class, have gone on to professors at Harvard, as well as Hopkins, Einstein, New York, etc. We also have now early investigators, and out of that program, we recognize that these postdocs, which were funded, but what happened when they're early R01s. And we recognize that the R01 issues, that the average age of an R01 was like 42, 43 years old. And certainly when I started, it was like 31, 32 years old. So that in my 25 years, it's migrated to this point where it's been very difficult for young people to get money. So we've established a program where we, through a jury, and now we have, I think, 16, 17 kids, I call them, but they're brilliant scientists who get about $1.5 million spread over 5 years. And what do we do specifically is they must work on things that are risky. We are not interested in things that are conservative, like, hey, I got a transcription factor, I'm going to do the same thing again and again, and we're not interested in that. We're strictly in high-risk research. And the success that we've had is, many years ago, I think Bob Pillay mentioned in 2007, Yamanaka, and showed that you could reprogram cells. Well, Kevin Egan, who at the time was a young assistant professor at Harvard, couldn't get funded. And Susan personally wrote her a check from the foundation to do his ALS work. And that got one of Time Magazine's Scientific Breakthrough of the Year. We've also funded a young investigator called Gap-Sang Lee, who's now at Hopkins, and he's leading an interesting program on this unusual disease called familial dystonia. Derek Rossi, who is this mRNA reprogramming, we also funded him. So we have the ability, through our juries and our contacts, we've recognized young, brilliant investigators, and we can identify them and help them out very early without going through this complicated NIH peer review process, which is still very good, but many times it's gone very conservative. So I'll tell you about the NICEP Research Institute, and that's really our intramural programs. Most people don't know that. Everybody thinks of us as a foundation that gives money. And Susan said, because her husband, Paul Goldgarber, was a really well-known Pulitzer Prize writer at the time, was writing for the New York Times. And they couldn't think of a name for the Stem Cell Foundation. And since he worked for the New York Times, he says, oh, just use the New York Stem Cell Foundation. And that is how we had that name. But we always think, people think of us as a a group that just gives money. But it turns out we have about 45 people in a building in Upper Manhattan that's probably one of the largest privately funded stem cell laboratories. 90% of our funding, 95% of our funding is derived from pure philanthropy. So from that pure philanthropy, we have the ability to do things that the NIH doesn't allow. For example, SCNT. I believe us and maybe the guys at Oregon are the only group in the United States doing somatic cell nuclear transfer. Dieter Egley, who heads this group, and Scott Nagel, another member of the group, are experts in this area, deriving ES cells. And last year they showed that a human oocyte was capable of reprogramming a human somatic cell. There's a technical problem with this. They showed that they could only do it by making it a triploid. But recent work, and hopefully in the near future, will show you that this is the triploid, and issues of that will probably be overcome. So we'll be able to completely reprogram using oocytes. And we're the only few groups who can do this because human eggs in New York State are allowed to be donated for this type of research. So we actually work on SCNT. We do a lot of ES derivation work, specifically in the areas of PGD. We're very interested in genetic diseases, and we're deriving embryonic stem cell lines. But the area that I got most interested is in iPS cells. Now, for those of you who don't know, I founded a stem cell tools company. And for 25 years, I've been involved in the area of kind of like cutting edge of biotechnology, primarily in the area of gene and cell therapy. Many of my colleagues are here in this room, as well as mentors, and so it's kind of fun to come back to San Diego in the area, specifically gene therapy. So when I saw that in 2007, I happened to see the Yamanaka paper because I had a heart attack. And I was laying in bed reading journals. And I said, well, wouldn't this be cool? And I said, my God, it's just gene transfer technology using transcription factors. Wouldn't this be the perfect way to start a company and or a tool company? Recognizing that tools companies were easier to start in 2008, I did that, and we raised a significant amount of money, and that company is now one of the major stem cell tools reagent companies in the United States in this area. But I got bored. Building a Home Depot is not necessarily the most interesting thing. I was really interested in how to apply the technology. And I'm also a human geneticist, for many of you who don't know that. I'm both a virologist as well as a human geneticist. And I was interested in these areas of how to apply iPS technology and combine my interest in human genetics. So one of the things we've done at the, leave that thought. We've made now, I don't know, 300, and all these are just iPS lines we've derived now using a non-integrating system. This is called Sendai virus. But we've also used this mRNA technology. These various diseases, we've characterized them. And we've done it in this one way that's kind of unique. We've taken this, and this is a process that I think Bob talked about, Pillay, where we take a bunch of transcription factors, throw it on cells, then you look under the microscope, and you hope you have these iPS cells. And it occurred to me that this is just a bunch of handwork, busy work. You know, when I was a student, you know, sequencing was handwork. And I remember people used to say, hey, maybe there'll be a machine that can do that. So that idea didn't escape my attention and the foundation's attention. So we decided that we could automate this, and we have. So we have now developed a turnkey system at the foundation that is using robotics, where we take a biopsy or a blood sample, and we take it from beginning to end, and all the way to, you know, characterization and freezing. Now we've made this massively parallel system. This is automated, like today. For example, today, nobody can get to the lab. The feeding is being done by automation. Now we have webcams on all the instruments, so we have people who are close to the lab, so if something gets stuck. It's not perfect, it's just parallel moving things in and out of incubators, and it's just an assembly line. So this is really, really important, because this now allows us to do a very, very critical experiment that I've always wanted to do in human genetics. I want to know what the diversity of mankind is. That's a real interesting question. I look in the room, and this is primarily Caucasians, and a couple Asians, maybe a couple Latinos. But I'm in New York City, it's very, very diverse. So we have set up protocols with the hospitals and clinics to collect a diverse number of samples. And these diverse samples are then banked to be reprogrammed. Why are we interested in this? One of the problems, and I'm also, for many of you who don't know this, I come also from the genome business. And that genome business has always bothered me. It bothered me because my good friends would say, hey Steve, we sequenced this. And I would say, well, I'm a geneticist. What does that mean? Well, there's a change here. So I could never ever link the genetic information, that is sequence information, to functional information. And I saw that the iPSTEL technology allows you to functionalize the genome now. At least certain pathways, certain genes. And it's really come to bear for us. If, for example, in a Parkinson's program, this paper's under review, so I can't really show it, but we've actually, by sequence information, we could not understand what the problem was. We knew there was there, but by functionalizing it through an iPS cells, making dopaminergic neurons, we could actually show what the problem was. That problem then would allow us in the future to screen a drug, because we now know what an issue is. So it's really, really important. So if you think about this, I have the ability now to massively array cells. We can do 2,500 cell lines in an 8 hour, in a year. We're going to probably ramp it up to 2 shifts, so we can do like 4,000, 5,000 lines. But we're really interested in this, and we have funding right currently to do 2,500. These are just normals, what we call them normals, genetically diverse. The things we're interested in, and I think this is going to be the future, is if we can make the right cell types, be it neurons, be it cardiomyocytes, be it the ultimate challenge of hepatocytes, I think we'll have the ability to put the human genetics in a box, and we'd be able to test things like drugs, etc. That's really the dream, and we're actually building the tools to do that. So it allows us to scale. Another thing we've discovered in many of the publications that we see are that the things are hard to reproduce. And constantly things are hard to reproduce. We think it's because of the few cell lines people study. We are now massively collecting cell lines for specific diseases like Parkinson's. We're not interested in genetic Parkinson's, we're interested in sporadic disease Parkinson's. We're interested in diseases where the genetics are unknown. So we think that with a massive array system, we can begin to do this. And I want to show you 2 things that's really, really important. Here's what we did with diabetes. Okay. We took and we can make islet cells. There's a company here in town that Paul Lincoln has called iSight, using their protocols, we make islet cells. But we took a very, very interesting experiment. It shows you the power of iPS technology. It's a monogenic form of diabetes. Okay, it's a genetic one. It's called Wolfram syndrome. That's all you need to know. It's a diabetes. What we did, and this paper's under review in one of the major journals too, is we made islet cells. We took those islet cells and we screened a library, a small known drug library. That known drug library gave us a hit. Basically, we showed we could reverse the Wolfram syndrome. This drug, these people die within within several months of age when they have the full-on disease. Now we have a molecule that's used in another disease, and we can actually test this in the clinic, and we're doing that at the beginning of next year. So it shows you the power of the technology. The technology allows you to see something phenotypically, make the right cell types, in this case, islet-like cells, and then screen those molecules. And we got lucky. We got a drug. We're going to take that into the clinic. This is with the Berry Center. We've shown we can make functional neurons. We have actually something we have also seen now using some of the sporadic Alzheimer's patients. We've seen things, phenotypes that are very, very unusual in culture. We don't know what it means, but we see differences. That's the key. We also are very interested in doing things with bone and engineering. I'm also, for those you don't know, I'm also have an engineering degree, and I'm very interested in bioengineering. And so we've been working with people to engineer bone using scaffolds. And this is an area that we have a paper that came out in PNAS in a year, and we've essentially translated this to a pure human system. We're taking human scaffold bone, put it in the bioreactors and making this, and we hopefully will test this concept in the clinic, or actually in large animals this year, and hopefully in the clinic. So I guess for a little group, we do a lot. We're only interested in experiments that we think are tipping point experiments. We're independent, we have no political or institutional agenda. We're not trying to make a profit, we're a foundation. We're interested in only one thing, is really how can we accelerate cures and take them into patients as best we can. So that's a little bit about the foundation and the research institute around. I live here in San Diego. I commute to New York every week, except for this week. I think it's going to be difficult. So but I'll be here for the whole meeting. Thank you very much.